Hello, we are Group 2, Richard, Dutch, Alex, and Cole. Our project is a model that predicts which domestic flights will land late, built for an airline's planning team rather than for passengers. Southwest is the case study. Delays are expensive, and when they happen consistently. In 2025, 22.3% of U.S. domestic flights arrived at least 15 minutes late. That 15-minute mark is the DOT's official cutoff, and it's the definition we use for the rest of the project. When a flight was late, it averaged 73 minutes late, and the FAA puts the yearly cost of all this above $30 billion. Southwest is why we framed it this way. Out of 7 million domestic flights reported to the Bureau of Transportation Statistics last year, Southwest flew 1.38 million, more than any other carrier. Their whole department runs on fast turnarounds, and there isn't much slack in the schedule to absorb a problem. December 2022 shows what one bad week does to that. Almost 17,000 canceled flights and roughly $800 million lost. So our question is whether you can flag the risk flights ahead of time before the day of travel while there's still time to plan around them. All of it is public, and we join 3 sources at the flight level. The backbone is the BTS on-time performance file, 1 row per scheduled flight with the carrier, the airports, the schedule, and how late it actually arrived, 7 million rows for 2025. Second is NOAA daily weather, rain, snowfall, temperature, and wind at 44 major airports, matched at each flight by airport and date at both ends of the trip. Third is the BTS T100 file, which reports monthly seats and passengers on every route. That tells us how big a route is and how full it runs. We limited the scope of flights between the 40 busiest airports. That's 3.3 million flights and half the year's traffic. And every one of those airports has a weather station on the field, so we aren't guessing at conditions. This slide is the one rule that shaped everything else. The model only gets information a planner would already have when the schedule was set. So it gets the schedule itself: departure, hour, day of the week, month, carrier, route, and distance. It gets that daily weather at the origin and the destination. It also gets each route and each airport's historical delay rate, which how big the route is, how full it runs, and how busy the origin is that day. What we cut is everything you only learn after the fact. The actual departure delay is the obvious one. If the model knows a plane pushback 40 minutes late, it predicts a late arrival almost perfectly and tells you nothing you didn't already know. Same story for taxi times, air times, and recorded delay cause codes. That call costs us accuracy, and we'd rather say so now than have it look like a weak result a week later. A model with leakage in it scores better and is worth nothing to the planner. On processes, we ran crisp MDM start to finish in a single Python notebook. We pulled a 600,000 flight sample for modeling, 480,000 to train, 120,000 held out to the test, stratified it to the delay rate, matches in both, with one fixed random seed so that the whole thing reruns the same way.
One of the clearest patterns we found is that delay risk increases throughout the day. At 5 a.m., only about 9% of flights arrive at least 15 minutes late. That rate steadily rises, reaching approximately 33% by 7 p.m. The main reason is that airplanes operate through multiple flights each day. If an aircraft arrives late on an earlier flight, there may not be enough turnaround time to recover before the next departure. That delay can then carry forward through the rest of its schedule. The snowball effect is important because late arriving aircraft account for 39% of all recorded delay minutes. So simply knowing the departure time gives us meaningful information about the risk of a delay.
Next, we want to see how much weather at the departure airport affects flight delays. On a normal dry day, roughly 21% of flights were delayed, but that number increased to 38% with heavy rain and 45% with snow. One interesting thing that we noticed was that the official weather delay codes do not tell the full story. Weather was listed as the official cause for about 6% of delays, but when we matched flight data with the actual weather information, we found that the weather played a much larger role. The main takeaway here is that bad weather at the origin airport can significantly increase the chance of delays. So when travelers are booking flights, looking at the weather of where the flight starts is just as important as checking the weather at the destination. For this next slide, we looked at how Southwest compares to other major airlines when it comes to delays. Although Southwest operates the most flights in our dataset, its delay performance is pretty average. Roughly 21.4% of Southwest flights arrive more than 15 minutes late, which placed them 5th best out of the 14 airlines we analyzed. Delta performed the best among larger airlines with a delay rate of just under 20%. We also looked deeper into Southwest airports and found that Denver is their busiest origin airport, with around 90,000 flights. However, Denver also had the highest delay rate among Southwest's major airport at about 30%. The big takeaway here is that delays aren't just about the airline. Things like the airport, the weather, and how much traffic an airport can handle all have major impacts. Southwest handles a huge number of flights while still keeping delays middle of the pack, which shows they are able to manage a large operation fairly consistently. This third slide compares the performance of our 3 machine learning models on a test of 120,000 flights. While logistic regression gave us a solid baseline, and random forest improved on those results, XGBoost performed the best overall. It had the highest AUC, the average precision, and F1 score. Since it consistently outperformed the other models and trained in about a minute, XGBoost is the model we would recommend for our deployment.
After selecting XGBoost as our strongest model, we examined which factors had the greatest influence on its predictions. Departure hour was the most important factor, which supports the pattern we just discussed. July was next, followed by weather conditions such as snow and rain at the origin and destination. The model also considers the airline, day of the week, month, and each route's historical delay rate. These factors all make practical sense, which is valuable from a business perspective. The model is not relying on mysterious or unreasonable relationships. Planners can understand why a flight is being identified as high risk and feel more confident using its predictions. To turn these predictions into something planners can actually use, we recommend a probability cutoff at 60%. At this threshold, the model flags about 23% of scheduled flights. Of those flights, 49% are actually delayed. This is more than twice the 23% base delay rate we would expect from guessing. The watch list also captures approximately 48% of all delays. On a typical day with 3,800 flights, this would produce a focused watch list of about 870 flights containing nearly half the day's delays. Planners could use this list to prioritize gates, crews, aircraft rotations, and passenger communication. The cutoff can also be adjusted. Lowering it catches more delays, but creates a longer, less precise list, while raising it creates a smaller list with higher confidence warnings.
Based on everything we found, here's what we would tell Southwest to actually do. We would tell them to run the delay risk score every day at the 60% cutoff and use it to place reserve crews and aircraft against the flights that it's flagging. Protect the morning bank first, since delays early in the day snowball, so fixing them before noon saves them way more trouble later in the day. We would make Denver the pilot station, since it's their biggest origin and their worst delay rate. So that's where this tool proves itself fastest. Tie weather triggers into the same system, so when rain or snow crosses the threshold, they staff up before the things fall apart, and then retrain the model every quarter. Since schedules and fleets change, an old model starts missing things without anyone noticing. Where this could go wrong. On ethics, the risk is someone using delay history to pull resources from cities that struggle, and that's backwards. The right move is adding buffer where risk is high, not cutting service. This also isn't a scorecard on crews or stations, since airports differ for reasons totally outside of their control, and a 60% flag is wrong about half the time on purpose, so the model suggests and a human still has to decide. On limitations, we use same-day weather that already happened, not forecasts, so a real version would be way less accurate. We only trained on 1 year of data and the biggest 40 airports, so new fleets or unusual years would need retraining for the model. And the biggest cause of delays, a late inbound aircraft, just isn't knowable ahead of time, so that caps how accurate any model like this can honestly get. What we took away from this, most of the actual work was data work. Cleaning, joining, and checking the 3 different sources took way longer than actually building the models. Leakage was our sneakiest problem by far, since the best looking features are often the ones you have to say no to because they don't mean anything real. An AUC of 75% sounds average, but turned into a watch list it doubted planning precision. So how you frame a result matters more than chasing a better decimal. And overall, public data's got us really far. 3 government data sets, no cost, and a model an airline could actually pilot.